Alright, in this video we are going to be taking notes over our mole to grams and our grams to grams. And so the idea and everything for today is to understand these Stoic conversions and being able to calculate them. Now, before we get into calculating these different things, we do need to review going over our molar mass. So just make sure and everything that the molar mass of an element is going to be the same as the mass on the periodic table. So while we're going through these questions, it'd probably be a good idea to have your periodic table out just to use that as a reference. Now, to calculate the molar mass of a compound, we are going to add up all of the masses of the elements in the compound. If any element has a subscript onto it, we multiply it by that number with the mass before adding them together. Let's go ahead and take a look at a few examples. And so our first one that we're going to have is going to be our MgCl. So we're going to go ahead and find the molar mass of our MgCl. So splitting this up, we're going to have our Mg. So our magnesium has a mass of 24.305. Our chlorine will have a mass of 35.453. So those numbers are just coming from the periodic table, and we're going to go ahead and add those together. So adding those together, we should get 59.758. And remembering that our units for molar mass are grams per mole. So our grams per mole are going to be the units for our molar mass. All right, let's go ahead and take a look at our next example. So our Na2SO4. Splitting this up, so I have my sodium, I have my sulfur, I have my oxygen. Taking a look at the periodic table, we should notice the mass of our sodium is 22.990. And from the subscript, I have 2 of them. So I'll multiply that number by 2. Next is our sulfur, which we have 32.066 listed as the mass on the periodic table, and I have 1 of them. And then our oxygen should be our 15.999, and I have 4 of them in this compound. Now I'm going to go ahead and multiply all of these out. So I should get 45.980 for my sodium altogether. Our 32.066 for our sulfur, and our 63.996 for our oxygen. Now that we have multiplied all those out, we are going to go ahead and add those together, and we're going to end up with 142.042, and that'll be our grams per mole. Now, I'm going to take this moment to also show a different way that we're able to set up the complete molar mass. So our units are going to be our grams per mole, but a little bit more of a useful way to look at it, especially for this topic that we're about to get into, is going to be setting this up into a proportion. So we're going to get 142.042 grams of our Na2SO4, and we're going to set that equal to 1 mole of our Na2SO4. So these two things right here are the exact same. They're just a different way to look at it. Now this bottom way is going to be a little bit of an easier way to look at it, especially when we talk about stoichiometry. All right, let's go ahead and take a look at our last example. So taking a look at our Ca3PO42, going to go ahead and split everything up. So I have my calcium, I have my phosphorus and oxygen. Taking a look at calcium, my mass should be 40.078, and I have 3 of my calcium atoms. Now looking at our phosphorus, our phosphorus should be our 30.974, and I have 2 of them. Now, remember that I have 2 because the subscript on the outside of the parentheses distributes inward, so I will have 2 phosphorus atoms. Now taking a look at our oxygen, should be our 15.999, And because of that 2 distributing inward, I end up with 8 of them. Going to go ahead and multiply everything out. So 120.234, 61.948, and 127.992. Add those together, and we're going to get the molar mass of 310.174 grams per mole. And that will be the molar mass of this compound. Alright, let's go ahead and take a look at our first stoichiometry problem. Alright, so this is going to be our mole to mass. So, if we remember from our last time, whenever we have an unbalanced equation, we need to go ahead and balance it. Now, looking at our rubidium plus our oxygen forming our rubidium oxide, we should notice that I have 2 oxygens on the reactant side, so I need 2 oxygens on the product side. Because of that, I will need to go ahead and put in a 2 in for our RBO, so I end up with 2 oxygens, but I also end up with 2 rubidiums. Needing to fix that on the reactant side, we will go ahead and put a 2 in for the RB. Now, whenever we have something blank that we don't change, we are going to go ahead and put a 1 in there. Now that we have balanced our equation, we are able to go ahead and take a look at the actual question itself. Now, this question is saying that we have 6.00 moles of our rubidium reacting with excess oxygen in the synthesis reaction. What mass in grams of oxygen reacted? Alright, so we're going to set this up very similar to our mole to mole problems. So we're going to go ahead and start with our 6.00 moles of rubidium. Now, setting this up in our chart, we are going to go ahead, set that up. We should remember that if I have the moles of rubidium on top, I should end up with the moles of rubidium on the bottom. Now, remembering from our mole to mole and looking at our mole ratio, looking at our balanced chemical equation, I have 2 moles of rubidium. And I'm going to set that equal to the compound that I'm wanting to really find. Now, in this question is asking for the oxygen reacted. So I have my 2 moles of RB, and I'm going to go to my moles of my O2. So the moles of the oxygen being what I want to find. Now, looking at the balanced chemical equation, I end up with 1 mole of O2. So I have 1 mole of O2, so I'm going to place that 1 mole of O2 right on top. Now, if I end here, I'm going to end in that mole of O2. Now, the question is asking for the mass. So we're trying to find the grams of our O2. Because of this, we are going to go ahead and we are going to expand the chart one more time. Right? I have the mole of O2 on top. Following the dimensional analysis trend, or the diagonal rule, the mole of O2 is on top, so on this next diagonal will be our mole of O2. Now, we may be thinking, what number do I need to put here? Now, knowing that we want to get to grams, so we want our grams to be the very end, we are going to go ahead and we are going to find the molar mass of our O2. Alright? So finding our molar mass of our O2, our oxygen being 15.999. I have 2 of them. So multiplying that out, I should get 31.998 grams per mole. Now, remembering that second way that we're able to write this, this will be our 31.998 grams of our O2 equal to our 1 mole of O2. So this 1 mole of O2 right here is going to fit into this spot. So we end up with our 1 mole of O2, which will be equal to our 31.998 grams of O2. Now, from here, I'm ending in those grams of O2, which is what I'm trying to find, so we're able to go ahead and solve. We're going to multiply the top, divide the bottom in order to get our answer, and whenever we do that, we should get 95.994 grams of O2, and that will be my answer. All right, let's go ahead and take a look at our next example. All right, so we are presented with an unbalanced equation, so we need to go ahead and balance it. We should notice right off the bat that our chlorine on the reactant side, we have 2 of them, but on the product we only have 1. To go ahead and balance that out, we're going to go ahead and put a 2 in front of the NaCl. We end up with our 2 chlorines and our 2 sodiums. Now, to balance out the number of sodiums on the product side, we need to go ahead and put a 2 out front of the Na on the reactant side. Then anything that we leave blank, we're going to go ahead and put a 1 out front. Taking a look at the question is asking how many moles of sodium chloride are produced when 58.2 grams of chlorine reacts with excess sodium. Now, this question is going to be the opposite of what we just did. So instead of starting with our moles, we are starting with our grams. So we're going to start with those 58.2 grams of our chlorine, of our Cl2. All right. Now we have our grams of our Cl2 on top, which means on the diagonal, we are going to need those grams of our Cl2. Now, the only number that will go with our grams in these types of equations is going to be the molar mass. So we are going to find the molar mass of our Cl2. So our chlorine itself has a mass of 35.453. But because it is our Cl2, I have 2 of them, we're going to multiply it by 2. And whenever we do that, we should get 70.906 grams of our chlorine equal to our 1 mole of our chlorine. So we'll put that number of 70.906 right here. And we're going to set that equal to our number of moles of our Cl2. So that will go right up here. So our 1 mole of our Cl2. Our next step. Okay, we're still not quite finished. We're going to go ahead and expand the chart one more time. We have the mole of our Cl2 on top. So on the diagonal needs to be the mole of our Cl2. Now looking at our balanced chemical equation, we are going to have our 1 mole of Cl2. So this will be our 1 mole of Cl2, and the compound that we are trying to get to is going to be our sodium chloride, which is our NaCl. Now looking at the balanced chemical equation, we should notice that we have our 2 moles of our NaCl, with that 2 coming from the coefficient. So that 2 moles of our NaCl coming from that balanced chemical equation. We are ending in our moles of our NaCl, which is what we're trying to find, so we're able to solve. We'll get 58.2 times 2 divided by 70.906. Whenever we do that math, we should get 1.64 moles of the NaCl as our answer. Now, these are the only 2 ways that you can be presented a mole to mass question. Either you're starting with your moles and you're going to grams, or you're starting with grams and you're going to moles. So these are your only two options, the only two pathways when you have a mole to mass stoichiometry problem. All right, now our next one, we're going to get a little bit more involved, and we're going to go from mass to mass. So we're going to go from our grams of one compound to the grams of another compound. Now we need to go ahead and balance out this equation. So always the first step is to balance the equation. In this case, I should notice that I have my 3 carbon on the reactant side, but only 1 on the product. So I need to go ahead and put a 3 out front to balance out our number of carbon. Taking a look at the oxygen last, we'll take a look at the hydrogen next. So 8 hydrogens on the reactant side, 2 on the product. So we need to go ahead and put a 4 out front of the H2O in order to get our 8 hydrogens. Now, we need to look at our total number of oxygens on the product side. So our 3 times 2 will get us 6. Our 4 times 1 oxygen will give us 4. So adding these together, I have 10 oxygen atoms on the product side. Now looking at the reactant side, I only have 2 of them. So our idea and everything behind this is what times 2 will get us 10. In this case, the number 5. So 5 times 2 will get us 10 oxygen atoms. So we'll put a coefficient of 5 out front. We're not going to put a coefficient out front of the C3H8, so we're going to go ahead and just put a 1 right there. All right, we have balanced our equation. We are able to go ahead and we're able to start the actual problem. All right, the question is how many grams of carbon dioxide are produced when 60.3 grams of propane burns completely? Now, whenever going from a gram to gram problem, we are going to need a little bit of space. These are the longest problems that we are going to have. So just whenever kind of planning out your writing strategy for these, just make sure you have enough space on your paper going from left to right. Okay, we're going to go ahead. We are going to start with our 60.3 grams of our C3H8. So our C3H8 will be our propane. We are going to go ahead, create our chart. We have our grams of the C3H8 on top. We know we're going to have our grams of our C3H8 on the diagonal. Now, remembering that the only number that will go with grams is going to be the molar mass. So we are going to find the molar mass of our C3H8. Right, so our carbon, the individual mass of our carbon is 12.011. I have 3 of them. Hydrogen will be 1.008, and I have 8 of them. We're going to go ahead and multiply all these out. So 36.033 and 8.064. Add those together, and we will get our 44.097 grams per mole. Now we're going to go ahead and put that number, that 44.097, into our spot. So our 44.097. Now remembering that the mass is always equal to our 1 mole of that substance. So we're going to go ahead and put our 1 mole of our C3H8 on top. Still not quite to the grams of our carbon dioxide, so we're going to go ahead and expand. All right, our next one, we have the mole of our C3H8 on top, which means on the diagonal will need to be the mole of our C3H8. Now, we're going to convert that moles of our C3H8 to the moles of our CO2. So right here, we are converting from one compound to another compound. So this will be the mole ratio coming from that balanced chemical equation. So looking at our balanced chemical equation, we should notice we have 1 mole of our C3H8, with that 1 coming from that coefficient. Now, we are wanting to go to our CO2. We're wanting to convert our C3H8 to our CO2. So on top will be our moles of our CO2. Now, looking at that balanced chemical equation for that mole ratio, we should notice it should be 3, with that 3 coming from that coefficient. So our 3 moles of our CO2. Now, ending here, I end with moles of CO2, which is not what I'm trying to find. So we are going to go ahead and expand the chart one more time. Now, from here, I have the mole of our CO2 on top. We know that we're going to have a mole of CO2 on the bottom. Now, we're going from moles to grams, so we're going to be using that molar mass. So down here, I'm going to go ahead and show the molar mass of our CO2. So again, our carbon being 12.011, I only have 1 atom of it. Our oxygen being 15.999, having 2. We're going to go ahead and multiply those out. And add those together. And we're going to end up with 44.009. And that will be our grams per mole. Now again, that per mole being equal to 1 mole of that substance, we're going to go ahead and put a 1 in front of the mole of CO2. Now that 1 mole of CO2 being equal to the grams of that compound, which is that 44.009. Now from here, I'm ending in my grams of CO2, which is what I am trying to find. So we're able to go ahead and solve this setup. So 60.3 times 3 times 44.009, all divided by 44.097. Whenever doing that math, we should end up with 180.54 grams of our CO2. And that will be our final answer for this problem. All right, let's go ahead and take a look at another example. All right, in this example, we have that unbalanced chemical equation again. We should notice we have 2 nitrogens on the reactant side, 1 on the product. So we're going to go ahead and put a 2 out front. We will go ahead, balance out the hydrogens, put a 3 in front of the H2, and then a 1 in front of the N2. Looking at the question, it is asking us to go ahead and find the number of grams of hydrogen that are required to produce our 15.0 grams of ammonia. Our ammonia being our NH3. So we'll go ahead and get started. We have our 15.0 grams of our NH3. We have grams of NH3 on top, so we need our grams of our NH3 on the bottom. grams, the number being our molar mass. So we need to go ahead and find the molar mass of our NH3. So our nitrogen individual mass is 14.007, hydrogen 1.008. Adding these together, we should end up with 17.031 grams per mole. Now that's 17.031 being placed into our setup. So our 17.031. Now the mass is always equal to 1 mole. So this will be our 1 mole of our NH3. Not quite finished with our setup yet. We'll go ahead, expand. We have a mole of NH3 on top. We know our mole of NH3 will come down on the diagonal. Now, at this step, we are converting from our NH3 to our H2. Looking at the balanced chemical equation, we should notice we have our 2 moles of our NH3, which will be equal to our 3 moles of our H2. Again, with that 3 coming from the balanced chemical equation. Now, we are almost finished. We need one more setup. We need to go ahead and convert our moles to our grams. So we have our mole of our H2 on top. On our diagonal will be our mole of our H2. So we need the molar mass of our hydrogen. 1.008 times 2 will get us 2.016 grams per mole. Now remembering that our grams per mole means that it is equal to 1 mole, so we're going to have our 1 mole of H2 on the bottom with our number on top. So that will be our 2.016 grams of our H2. Now we're ending in the grams of H2, which is what we are trying to find. So we are able to go ahead and solve. We'll get our 15 times 3 times 2.016, all divided by 17.031, which will get us 5.33 grams of H2 as our answer. All right, let's go ahead and take a look at just one more example to make sure that we fully understand. All right, so we have our Cu plus our AgNO3 forming our CuNO32 plus Ag. We need to go ahead and balance this out. We'll go ahead and put a 2 right here, a 2 right here, and then everything else will be a 1. All right, our question, how many grams of silver are produced when 65.0 grams of copper is added to silver nitrate? All right, so we have our 65.0 grams of copper that we're going to be starting with. Putting into our setup, although let me fix my copper really quick as it looked almost like calcium. So our copper, so our 65.0 grams of copper. We'll go ahead, grams of copper on top. On the bottom will be our grams of copper. Now, in this case, our copper, we're just going to look at the mass on the periodic table. So if we look on the periodic table, the mass of our copper is 63.546. Now, the mass is always equal to 1 mole, so that 1 mole of our copper is on top. We'll go ahead expand our setup. We have our mole of Cu on top. We are going to have the mole of Cu on the diagonal. Now at this point we are going to convert from one compound to another, or one element to one element in this case. So we're going to go from our copper to our silver. Looking at the balanced chemical equation, I have 1 mole of copper, which is going to be equal to our 2 moles of our silver. Again, taking a look at the balanced chemical equation in order to figure out that mole ratio. We're not quite finished yet. We're going to expand this one more time. Now taking a look, I have the mole of Ag on top. On the diagonal, I know I'm going to need the mole of Ag. Our molar mass is always equal to 1 mole of itself. And then on top, we're going to go ahead and take a look at the mass on the periodic table. And the mass of our silver will be 107.868 grams of our Ag. We have now completed our setup and we're able to go ahead and solve. We'll multiply everything on top, so 65 times 2 times 107.868, and then divide all of that by 63.546 in order to get 220.67 grams of our silver. And that will be our final answer.